Hi, I'm Luke Barrett. I'm a member of IQT Labs. Recently, I've been working on a project which automatically records airplanes as they fly overhead, and I've ended up with way too many photos of airplanes. So what I've been putting together is a simple object detector which can help go through the different photos, find out which ones actually have airplanes in them and which don't, and locate the airplane in the photo itself using straightforward object detection. So what I'm going to be going through today is how you can build a custom object detector using transfer learning. I'm going to be working with airplanes today, but the processes and scripts in these Jupyter notebooks could easily be used for building a puppy detector or a coffee cup detector. As long as you have some labeled data, essentially pictures with bounding boxes around them, you can easily turn that into an object detector to detect any sort of object, really. And since you're using transfer learning, you don't need tons of images to get started. I'm using about 500 images. I went ahead by myself, just drawed some boxes around airplanes. Took me about 50 minutes or so. So it's pretty quick to go build up your own custom data set. So let's go dive into the code. So to get started, let's see, first fired up, you'll end up here. Just go into the notebooks folder, and we're going to start by creating a data set in voxel 51. So open that up. Voxel 51 is a nice little data management platform. Makes it easy to build machine learning data sets and then export them into different formats as needed. So we'll get started there. I already have a directory mapped into the container called testing. It's just filled with lots of photos of airplanes. So this will just run through what to do to import this into a data set inside voxel 51. I'm calling this data set test data set. Pretty creative. So we'll get the required libraries we need. 51 is voxel 51's library. Here is a small function. It basically goes through all of the JPEG files in a directory, and I have a simple naming convention. It sort of attaches an airplane identifier, and that airplane identifier is part of the file name, and that's used and imported into the database as a field, just so we can use that later on. So we'll just load that function in. Next comes creating the data set. So what's happening here, you can see some of the progress. So it goes into the directory. Well, that was pretty quick. They'll go through all the images in the directory and load them one by one as samples into that voxel 51 data set. Oh, so it's still running. You can see in the code, pretty simple stuff here. It goes up to the build image list. That will give you a list of all the files that are in that directory, and along with their external ID. So that will return that list, and then it will go one by one through that list. You could easily extend this to really work with any sort of directory filled with JPEG images, and this will just load them into a voxel 41 database data set. So if you're doing this, you may want to change external ID. You may just want to get rid of it altogether. You remove that as a field here. And the other option too is maybe you want to come up with your own sort of metadata, import that from the file names themselves. So we'll take a quick pause here and come back when this is done running. Okay, welcome back. Ooh. So the good news is it's completed uploading, not really uploading, adding all of those files into a voxel 51 data set. So we're good there. We have our files loaded up. The next step is to open a new notebook. So let's go back here. We now want to go to upload from voxel 51 to LabelBox. The next step is to go and apply or add really bounding boxes around all the airplanes in the photos. So I'm not going to actually run this script all the way through because I'll just sort of walk through the code because I already have a labeled data set and I don't want to go through that process again. But we'll just go through the gist right here. And for people not familiar with LabelBox, it's a hosted service that makes it really easy to label your data. Has a nice user interface for that. It looks like Voxel 51 also supports a number of different annotation providers, so you can use those too. So I'll just sort of walk through the configurations you need to do here. Remember, we came up with the Voxel 51 dataset name. It was test dataset. So you just change that and update it to whatever name you're using there. In LabelBox, you'll already have had to go into LabelBox, create a project and a data set associated with that project. Those can both be empty, but you'll want to provide those names here. And finally, you'll need something called a LabelBox ID field. This is used by Voxel 51 as it sends up different data or samples really up to LabelBox. Every time it's done uploading one, it will get back the LabelBox ID once the upload's complete. And you can store that here. That's useful when you then go back and pull down the labeled data. It can reestablish that association. The last thing you're going to need to add is you'll get through the LabelBox interface an API key, and you can just cut and paste that here. Let me correct that quote, make that all nice. So that's what you have to do for configuration. You go through and do that. The code here is really simple. First thing it does is it pulls up that Voxel 51 data set. It then goes and retrieves, based upon your LabelBox dataset name and project name, it will pull down the actual long, non-human readable internal ID that's used for both of those. And it just retrieves that through the LabelBox API. So when you have that, you'll end up with all of the information you'll need to just make one function call, essentially, down here. The first thing you're going to do is you're going to likely want just a subset of the overall data set to send in for labeling. We're going to be doing transfer learning, so you don't actually need that many images with annotations on them. So I went for 500. You can adjust this number here. 500 may be overkill. It may not be not enough. It may not be enough. So adjust that based upon the data you're using. But essentially, with a shuffle, we'll take a random sample from the larger data set that you've created in Voxel 51, and then we'll take 500 of those, and then we'll make this function call, which will upload those photos associated with the different samples you've selected in Voxel 51, and it will send them up to the LabelBox data set that you've specified up above in the configuration. For each successful upload into LabelBox, it will get back that external ID and then save that back into the Voxel 51 dataset. So we'll pause here and we'll pretend this is all happening in the background. So let's take a quick break. Okay, welcome back. So during the break, you would have been going inside LabelBox, labeling all of your objects. After that, you'd then go and hit export and download a nice JSON blob. That blob would have all of those assets, the labeled assets you just labeled, so the bounding box is associated with the file name, and along with a URL to download that file name. So let's go and pull that into a Voxel 51 dataset. So we'll go open up the export from LabelBox to Voxel 51 notebook here. And we'll start doing some configuration. What you probably should do behind the scenes is download that JSON file and upload it up onto the computer running your Jupyter Notebook. You'll want to get it into that notebook subdirectory. It's mapped into the Docker container, and it makes it easy to pull it in inside the container. So gone ahead and done all that. That's the file name I'm using. What I'm going to do is import it into a brand new data set. So this will just have the labeled images in it. Remember, it's 500 out of the total 42,000 I think I imported. So we'll just call this labeled data set. And since we're creating a brand new data set, not joining the information back into that existing data set, this LabelBox ID field won't be existing because we're not, that's used to merge between voxel 51 and LabelBox. But we'll keep that name the same. So let's go ahead and run this. So we'll do the imports. We'll load that voxel 51 dataset right here. And I guess we won't. Okay, let's take a brief pause. Okay, welcome back. So we figured that one out. So the problem here is I'm trying to load a data set before it actually exists. So what I'm going to go do is borrow a little code from right here. This was in, remember how we created the data set? So what this will do is it will first try to create a data set. If that already exists, then it will load it. So this will give us the best of both worlds. Let's give this a try. Okay, so we created a brand new data set. Perfect, that's what we wanted to do. The next step is to add a field. This is the LabelBox ID field. Since it's a brand new data set, it doesn't exist yet, so let's go and add that in. Otherwise, this next step will complain. So now we're going to be downloading all of the images from LabelBox into our voxel 51 data set. It's actually going to be pulling down the media that we've uploaded into LabelBox and adding that into the data set too. So when this is all done, we should have about 500 images or so with labels attached to them in a brand new shiny data set. So let's take a brief pause and we'll come back to this in roughly 1.3 minutes. Okay, and we're back. While we're away, completed the download of all that information from LabelBox into our brand new data set. So let's launch a voxel 51 window and explore some of that data. Voxel 51 has a bit of a user interface. It lets you view and select samples from your data set, but you can't actually do anything with that. You have to go back to code essentially to make any changes based upon that. So let's just pull up their interface. It's at port 5151. We can browse through our labeled data. That is great. See little planes, little boxes. Life is good. So it looks like we should have something we can train on. We'll notice some of the ones got skipped with no bounding boxes. There'll be some good training fodder there. Perfect. Okay, let's close this down. Go back to our notebooks. Remember the name of this data set. It's labeled data set. And let's pull up train plane detection model. Excellent. Okay, so this will take a bit of configuration. So we'll sort of walk through these different steps. We're going to be using TensorFlow 2's object detection API for doing this. So as I've gone through this, I've tried to keep track of where I pulled different tutorials from, and different good things to check out as you go through it. So we're going to start by coming up with a training name. This is just the name that will be used to help differentiate the different training runs you might do. So if you want to come back and use a different model, it doesn't clobber the one you've trained before. So the label field we're going to be using, I forget. Let's go. Easy way to check this is if we go back to our voxel 51. There it is. It's called detections. So detections is the name of the label we used for the different bounding boxes. So it's an easy way to check that. So we'll put detections here. And dataset name, I already forgot. Okay, let's go back to here. And it is labeled dataset. So let's go choose this. Okay, and we're going to be doing transfer learning. So that means you start with an existing pre-trained network with some of the weights already in it. It's been run and trained for a long time against ImageNet or maybe the Cocoa dataset. Looks like this is the Cocoa dataset. And all you're going to be doing is locking most of it and then retraining the last few rows. So you need a lot fewer training iterations to get it to work well. And to do that, you have a number of different choices you can make. You can use MobileNet network architecture. There's efficient detection network architecture, and then there's different sizes and configurations. We're going to keep it really simple. We'll go with MobileNet with an SSD feature extractor and go with version 2 of that. You can Google most of these things. These were just sort of the standard default configurations. And this is the choice among some of the pre-trained models that the TensorFlow crew has made available. So we're going to want to make a choice on our model detection, our model configuration. We're using SSD MobileNet v2. So we go down here. It looks like it's already filled in, but we'll just put that there. We're going to go for 40,000 training steps. Seems like a good number. You can check things out in TensorBoard. It may be overkill. You can adjust it in subsequent runs, but some of the different model architectures need more training than others. Some have taken larger images too. So let's see. We'll go run that step, pull in all those configs. The next step just fills in and creates some additional constant values there, different paths that we'll be using based upon the training name you specified up above and the model configuration you picked out. Load those in. We're also going to install a couple of different libraries that might be necessary for voxel 51 to work, and then the ever helpful wget. And then, so the next step is we want to download and install the TensorFlow model. It's a different repo than TensorFlow, and that's where you'll find the TensorFlow 2 object detection API. It's in the TensorFlow models repo under research. So pull that down. The next step is then it has a number of proto buffs inside, so you're going to get those all built out nicely and do a pip install for all the required packages that it needs. This takes just a little bit of time here. We'll just take a short commercial break. Okay, we have that complete. Excellent. Read through just does a lot of stuff, installs a bunch of packages, and that's great. Gives you a little error. Anyhow, moving on. Next step is to import a bunch of libraries. That will get us set up for later, and start to get matplotlib ready for some inline graphing. Excellent. So we have a lot of our imports taken care of. We have our libraries loaded. Now it's time to pull in the data set we're going to be using. So we load up our voxel 51 data set right here. Get that started. Let's just take a sneak peek and explore what's in that data set, make sure it matches what we were expecting. Good. So we can see their images. Great. We have 465 of them, which was about what we expected. And they do have that detections field that we specified up above. So that's good. And here's a sample of one of those records. You can see, the bounding box labeled with plain. So perfect. Okay, so the next step is to export from voxel 51 into a TensorFlow record format. So I'm just going to get that started while I talk about it because it takes a little bit of time. Actually, it doesn't because we only have 500 images. But TF records or TensorFlow records are a way of putting together in a single file a bunch of images and their associated bounding boxes or labels. Makes data sets a little more portable between machines, and it bundles everything up nicely. And more importantly, the object detection API expects the inputs to be in a TensorFlow record format. So if you want to use this easy to use method, then you got to get it in TensorFlow records. Okay, so we have our training data ready to go. The next thing we need to do is prepare a list of the labels that are expected in the correct format. So there's some nice utilities that make this a bit easier to do. And I've included a couple functions if you're either doing classification or if your label field's a detection. So as we saw above, the label fields we had were for object detection. So we'll run this function, and we'll get away with a single value plain. We can then use this convert class function, which pulls in just some simple libraries to give us the text file we need, which just describes all of the different labels. So the final output from all of that is this simple file, which just says the name of the single label we're using is plain, and the ID associated with it is 1. Interesting note for MobileNet, the ID of 0 is reserved. That's used for the background. Found that out the hard way. So you always want to start at 1 if you're going to be training a MobileNet model. Okay. So now we're going to pull down, remember we're doing transfer learning. We're going to pull down some of the pre-trained models. The one we're using, which is MobileNet v2. So it pulls down that model along with the saved weights and a checkpoint for that model. So you can essentially rehydrate the model, have it fully trained, ready for munging with some new objects to detect. We're also going to download a configuration file that's associated for that model. The configuration file gets fed into the object detection API, which are really just a bunch of Python scripts, and it tells the different settings to use during training. So let's see. Let's go and configure that configuration file. The first thing to do is just make sure we can parse that labels file. There's, as it says correctly, one class we're working with, plain, but that confirms with where we are. And the next thing we want to do is just edit and make some changes to the configuration file, the default one we downloaded from Tensorflow's GitHub, just to make it, to set it up to do some transfer learning. Then also change it to point it to where the correct files are. So we change some of the paths around. And right here, the label map path, say that 10 times fast. That's the simple text file that we mentioned up above. It just has plain and 1 in it. The batch size and the number of steps, those were at the very beginning. Remember, that's about 40,000 was what we were going for. Step size of every 500 images, it will go and check and see how it's doing. The learning rate, I found this out the hard way. If you start training, things go sort of crazy and your loss rate starts to climb instead of go down, it's probably because your learning rate's wrong. So I've set it to be essentially decimal point 0.008. That seemed to work well for the images I was training with. You may need to adjust this if you notice that your loss rate as it begins to train is not going down. This is a good place to start futzing with. And then there's also the concept of a warm-up learning rate, where it starts out slow, a very low learning rate, and then increases it as you get over sort of the number of warm-up steps. In this case, 250 or 2,500. Also added in under the number of classes, we just set that to be 1. And then I've also added in to use, instead of using SSD random crop, which is one form of doing data augmentation, to instead use random crop image. And since I'm working with very small planes, it does a good job of cropping in sort of a zoomed in view of the plane image and doing this randomly just to give you more variety in the data you're using for training. And then the final part is to just point to the checkpoint value you're going to be starting from, and actually to change that from being classification to be detection. So we'll run through all this. It will go through the configuration file, make all of those changes, and give us a brand new one. If you want to check that out, here is what the final configuration file looks like after we've done those substitutions. People way smarter than me can probably make some additional changes and do some additional tuning. This generally seemed good enough to get really good results. And there's slightly different configurations for the different models up above. So, that's that. And so the final step to start training is just to make a call to this Python script, which is how the object detection API goes about doing training. You tell it the path to that configuration file we went through above. The model directory that's where we saved that downloaded pre-trained model. The number of training steps, remember that was about 40,000. And the evaluation steps, I think that was the 500 there. So we're just going to run that. We'll stay on the line a bit more until this gets started, just to give you a sense of the voluminous amount of information that gets spit back. We're training this on a rather beefy machine. It has 3 GPUs on it. And one of the nice things about TensorFlow 2's object detection approach is that it can make use of multiple GPUs a lot better than the object detection code that was in TensorFlow 1. That code, the older code, was based upon something called TensorFlow Slim, and that's wasn't as good at being able to take advantage of multiple GPUs. The newer model in TensorFlow 2 is built upon Keras, which has built-in support for using multiple GPUs, so you get a nice speed bump from that. So as the jobs start getting distributed, we load in and we start reserving some time on those GPUs. And then lots of other things happen. I really can't parse all of this. A lot of word stuff about depreciated code, things not working in the future. So, that's to be expected. And if we pause a second, we'll just wait a second until we start seeing some of that training information come live here. So continuing to scroll, these are just some feedback. It's gone through and loaded up the model itself. You can see, here it's not finding the exact type things it wants. But again, these are just warnings. You notice that it's still happy and doing something. Keep scrolling through this output. And I think we're almost to the point where we'll start seeing some training success. Let us pause for a second. And really, in reality, this is, for me, been most of what machine learning is. It's just running some things, getting a lot of output you don't fully understand, and then waiting, hopefully, for some success. And we're continuing to see more output. I always forget how long this actually takes to actually get going and start the training process. So we're going to be going through, about 40,000 steps, and I think the batch size was about 500 images, if I remember correctly. Oh, perfect. So it takes a while. I think this would take about, it looks like we can get about 5 steps. If you look at this, the per step time takes each step is about 0.2 seconds. So you can get about 5 steps done a second. So we're about like 2 hours or so to go through this full training cycle, but it's working, so that's good. So let's parse the output a little. So we have it set to print out status update every 100 steps. You'll get how long it's taking to go through each step. Loss, which gives you a sense of how well the model's training. And that's about it. You can do some additional things where you can launch TensorBoard too if you want a little deeper insight into how well your model's working. But in general, this is decent information. So what we'll do is we'll just pause here, come back in 2 hours or so when this is done training, and then walk through how you could evaluate this trained model when it's done. So let's leave it here. Okay, here we are. Just completed about 40,000 steps of training, so that's good. And we got loss down, seemed to continually drop the entire time, so probably another good sign right there. But The good news is we have a model. So let's see how well it works. Let's move on to evaluate trained model. So what we're going to do right now is load in a few imports, get some libraries, some helper functions, which will help us load in some raw images. And also, let's take a look at our model directory, see what all that training generated. So you can see in the directory, we set aside for that model as it trains. We have a number of checkpoints. Checkpoints are saved periodically. And we'll just want to note here this number 41. So we'll take that. And it looks like this configuration step's already complete, but you could restore it, the model from different checkpoints. So if you noticed, for some reason, things were dropping off the cliff, you're hitting some weird local minimum or maximum around some point, you could restore from checkpoint 36 if you wanted instead. So anyhow, we're going to go and restore the model from checkpoint 41. That was the final checkpoint. Get that all set up. So it will say, let's go from checkpoint 41 and give it the checkpoint file. You tell it the configuration file you want to use, and which also points to the model you're going to be using. So you give it all of those things. This just helps us restore the different labels we're using from that label map file. Remember, it's really just plain, but in some cases you might have something a lot more complex. That just helps you load up that file and get the label to the label number mapping correct. And finally, before I run this, we'll just sort of walk through what happens here. This loads up an image. It picks it randomly. I have just a directory full of lots of plain images. It will just pick one of those. It will then, we'll start this running. It will then just pick one at random. It will pass that image, where find the right spot for that, pass the image into detect function. It will pass it through that model we've loaded. Then finally, so here it's loading this up, it will display a picture of the image, overlay a bounding box of where it thinks there's a plane, or you may find more than one plane, and show that to us. So here's the different predictions it made. So if you look right here, I won't reveal it yet. Get 90% confidence on one of those. That's a good sign to found a plane. Let's scroll down, and here we have it. We have a trained model that's able to detect planes based upon feeding in 500 images with bounding boxes that I personally drew by hand onto them. We were able to come up with an object detection model, which is pretty amazing. So that's great. Looks like we have a working model. You could do something a lot more scientific here, run it against a lot of images, and come away with some better sense of how it's performing, but looks pretty good. Let's ship it. So moving on to exporting the model. The model TensorFlow Object Detection API provides also a couple functions for saving your model. Actually, it's the exporter main v2 script here. You just pass it, again, the checkpoint you're interested in using. Again, we're going with 41. The configuration file, which points to the model you're using, and then just the directory you want it to spit out at. So let's just go do that. That will combine those checkpoint weights with the model and give you a TensorFlow saved model. So it's a lot more portable. It gives you a single file you can transport around, and lets you load it up into standard TensorFlow workflows. So while that's doing that, I'll just sort of preview some of the other things you can do too. You can also export it into a TensorFlow Lite format, which is better for running on mobile devices. And using the TensorFlow Lite converter too, I have a Python approach for doing this, which is compatible with exporting it into, or compiling the TensorFlow Lite file into a format that the Coral Google Coral development board likes too. So you could also run this on a Google Coral board and run at the edge. It should be noted that the Google Coral is really only happy with the MobileNet SSD format. It can't really convert the FPN or the efficient DET networks. So if you're going to go target the edge TPU, make sure you're training against the MobileNet SSD V2 model we use today. So great, let's just check. That looks like it completed, spit it out a model. We have one other type of export I'm going to run you through here too, and that's if you want to convert it and run it in your browser. The TensorFlow JS is the way to do that. So to get started, you'll just pull in TensorFlow JS. Great. Then you can just run the TensorFlow JS converter. Give that a little bit of time, and that will split out a version of the saved model from above into a format that TensorFlow JS can pull in. How to actually use that is a talk for a different time, but while we're doing some conversions, I thought I would queue that up. So you get a lot of the similar output here. It's going through and doing a number of different optimizations, trying to create a nice, small, compact model, because you're going to be shipping this. When you use it, you ship it over the internet from server to browser. So if it ends up being 250 megabytes, that is a lot of download. Let's give this a sec. Keeps doing optimizations. This is great. Okay, now it's writing the weight file into a big JSON blob. And one of the other things we can do, just helpful, is also take a look at that saved model file from up above and sort of see what the different inputs and outputs are. Helpful if you're going to try to pass data in or you want to access the different output tensors. So you can see you have some different detection boxes it detects, the different classes associated with the detection boxes, and sort of the confidence scores here. So that is that. Let's take a short pause here, and then we'll go take the final step and run this model against all of the 40,000 plane images we have in our voxel 51 dataset. Okay, now that we have a trained object detection model, let's try applying it to some of the 40,000 or so plane images we have and see how well it does at detecting them. So the first step in doing that is just filling out the configurations correctly. You want to update the paths. This is where you'd fill in the training name you used back here. Training name. So take that, fill it in here, and also here. And we're going to want to use that original data set we built with all those images in it. That was called test data set. And finally, the field name. This is the field in voxel 51 where the results from running object detection will be stored. And again, image width and height, that ties back to the size of the image that the object detection model expects to have for input. For MobileNet V2, it's 320 pixels by 320. When you start using efficient detect, it uses higher resolution, so you might have to update that there. And we'll then load in our data set. This will spin up voxel 51. Next, we'll just import a bunch of different libraries. Now we're going to go load the model we had saved earlier. This will just take the TensorFlow saved model and saved in the TensorFlow saved model format and load that up. You can see it takes a bit of time because the models are pretty large. So let's see, done in about 17 seconds. The next function is just a little helper. It will load an image off disk and put it into a NumPy array. Finally, just a little helper class here that will help go through and pull out a class ID for a given name, or give you a name for a given class ID from your label map file. Now let's kick this off and then sort of walk through what it does. So first it pulls from the data set all those images. Oh, looks like we still have a little bit of an error. So hold on a sec while I figure out what's going on. Okay, got things up and running. Turns out all I had to do was go into back here, go to kernel and shut it down. Looks like it was still using some of the GPUs and not doing a good job of sharing that. So when I tried to use GPUs over here, something barfed. So it's a good reminder just when you're done with a notebook and moving on to the next, just to go to kernel and shut down. So you can see it's going through, still running, going through each image, running it through the model, getting detections back, and applying those into voxel 51 with the results. So adding those bounding boxes back onto those images. And if you look at about how long it's taking per image, and considering we have 40,000 images, this could take a while. So we'll let this just keep running. But we can probably just wrap it up here. When you're done, you just go down here to examine the results. That will let you just see how well you did with the bounding boxes, and then you can go down to view results too and pull up your whatchamacallit to pull up the voxel 51 web interface over here. So since this will take roughly all weekend, we'll just stop here, and we'll have all of the links down below so you can click through, get the code we're working with today, and have some contact information down there too if you want to drop us a line if you have any questions on how to do this. Of course, it's all up in GitHub, so create an issue if you find anything wrong or have better ways of doing this. Please let us know. Thank you.